There we go. Okay. So I think we got it connected now with audio. Alright, so that's good. Okay, we're good. Alright, so I'm gonna close my monitor. And okay, so thank you for the confirmation. Alright, so I'm not gonna use any more time, to show Joplin. And instead, for all the in-class examples today, I'm gonna use Joplin. So there we go. Oh, reviewing the homework. Sure, that is perfectly fine. Let me go take a look at the homework. And that's for propositional logic. And it is, let's see, which one? Resolution and proof by contradiction. There we go. Alright, so let's check out. Okay, so there are two proposed theorems. The first one is T implies S and R, and then the second one is Q and R implies T. Those are all the proposed theorems. Okay, some resolution here. Oh, this would be perfect. This is perfect for Joplin, right? Because I can use Joplin now. Yay! Okay, so copy and paste into Joplin. Okay, so I'm gonna do a homework review. So on the left-hand side, what you see is Markdown, which is a as opposed to markup language, this is a markdown language. It's a funny name, but basically this is a quick and easy way for you to use a plain text editor to create a text file that can then be formatted into HTML easily. Alright, so I'm gonna paste what I copied from the other side, and then we'll start to work on it. Alright, so with the notation that I have chosen to use, there's no need to use math equations, simply because there's no special symbol to use, and that's the reason why I want to use this particular notation. So the first one is this one that I want to show you guys. So we have to convert this. We have to first negate it, because the whole idea of proof by contradiction is you do not start with the proposed theorem itself. You start with the negation of the proposed theorem. So we're gonna say, okay, so we'll say negated proposed theorem is gonna be a negation in front of this entire thing. And this is also the reason why I do not use the math notation for negation, because this one is a whole lot easier to type. It's just an exclamation point. And now we're gonna, okay, so it doesn't like it because it thinks it is, I think it's the exclamation point. The exclamation point is making it think like it is probably a header of some kind. So we're gonna do it in plain text mode. So this is verbatim, and then we are gonna expand this. Now this is negated, okay? You see that sign? Okay, so now the next thing we need to do, it's not lined up. All right. It's still not lined up. That's okay. So the first thing we do is to get rid of the implication. The implication is the negation of the left hand side, and then we have an or of the right hand side. So at this point, I just want to re-emphasize, we talked about this already, but the operator priority is preserved. So in normal notation, addition has a lower priority compared to multiplication, and since conjunction is borrowing the notation of multiplication, it preserves the priority of that operator. So we'll put an equal sign here. Okay, so there we go. Alright, so that's just the definition of implication. And then what we'll do next is to apply De Morgan's law, because this negation on the outside is going to be distributed into the inside. Phi and psi to symbolize. It's not necessary, but if you want to map it to what we have talked about in class, this is basically your psi. So if you want to, you can say this is psi, and psi is the one representing all the things that are known to be true. That's how I use psi in class. So the Greek symbol won't show up unless I turn it on. So this is basically psi, and what we see here, this is basically our phi. So phi, and this is the first one. So I'm gonna say phi 0, phi null is that expression, and then close the math equation. There we go. All right, and obviously the right arrow can be fancier, so we'll use this is a right arrow. There we go. All right, so there you go. Super fancy right there. All right, so Chris said, I don't understand how you could choose that as psi. How does it relate to the theorem? So in class, we used psi to represent everything that is known to be true. It's basically the CNF of everything that is known to be true, which starts with everything in iota. And in this particular assignment, it was assumed that we start with the expression that was given to you in the previous assignment, and in the previous assignment we ended up with this particular CNF, and that's why it is psi. So in class, okay, it's just that we used the psi, the Greek symbol psi, to represent everything that is known to be true. It's not the theorem to be proven. It is just all the axioms. And what Armand is talking about is to maintain that consistency with how we used psi for that purpose and how we use phi to represent a theorem to be proven one way or another. So I hope this is going okay, and we're continuing with the derivation here. So now we need to do a De Morgan's law. So De Morgan's law is distributing negation into the inside, and it will also change the operator from a disjunction to a conjunction in this case. So now we have not t, and then the other side is the negation of SR. So it is really important to maintain extra parentheses in this case, because the negation is applied to S and R together. It is not applied to just S. Okay, so it is important to use parentheses around it. And then at this point we simplify. So on the left hand side it becomes just T, and then on the right hand side we apply De Morgan's law again. So now we have not S or not R, and we have our CNF. This is a CNF because we have two terms in the conjunction. T by itself is one term, not S or not R is the other term. So do we have any questions about how I derived the CNF of the negated proposed theorem, known as phi 0 in this case? That's just a label. I mean, phi 0 is really just a name. It has by itself it has no special meaning. All right. Okay, so what we need to do now is to perform resolution. Well, before we perform resolution, we're going to have to make a quote-unquote super CNF, which is the concatenation of the CNF of everything that is known to be true, which is known as psi in this case, and the CNF representing the negated theorem, which is known as phi 0 in this case. All right. Distribute T, because if we distribute T we end up with a non-CNF anymore. This is a CNF. I said add. I'm not sure what you mean by that. Okay. All right. So this is a CNF at this point because T is one term, and then the other term is not S or not R, and then these two are connected by a conjunction. So we have a CNF representing the negated theorem. So now moving on to the I'm going to put it in quotes, super CNF. So super CNF is basically, in this case, I'll use the math symbol first. So it is psi and, okay, so just to be very clear that we have a conjunction here. This is psi and phi 0 or phi not phi null. So negation of phi null. There we go. Alright, so the super CNF is essentially representing this, but because psi is already a CNF, and then not phi 0 or not phi null is also a CNF, we just have to concatenate the two CNF and join them by a conjunction, then the result is also going to be a CNF. Alright, so let's do some copying and pasting here. So we started off with this one here. It is already a CNF. Okay, so we got a copy, and let me count the number of spaces because I think I need at least 4 for it to use. Basically, it's a pre-formatted symbol or pre-formatted line. There we go. And then we're gonna concatenate it with t as one term. The parentheses are not needed in this case, but I'm just gonna put it here just so that we understand that this is its own CNF. I mean, its own term in a CNF is a disjunctive term in a CNF. All right, and I flipped the order of the R and the S, just so that it is alphabetically sorted. All right, so we have this. We are starting with this, and now we want to say, okay, what can we do with this, right? So we want to do resolution. When you are performing resolution, you're looking for two disjunctive terms where one has a non-negated variable and then the other one has the negated version of the same variable, but just one. Okay, you cannot do two variables at the same time. Just if there are two where one side is negated and the other side is not negated, pick one. Okay, you cannot have both at the same time. Alright, so it all depends on whether you want to do this. I'm going to do this systematically. So I look at the first one and I say, can it resolve with the second one? The answer is no, because the second one doesn't have a Q, does not have a R, and does not have a S either. And when I say Q, R, S, I mean the non-negative version. So it won't resolve. And does it resolve with this one? The answer is no, it does not resolve with that one because this does not contain anything that mentions Q, R, and S. And does it resolve with this one? The answer is also no, it does not resolve with this one because it does not contain any Q, R, S non-negated. Alright, so we are not giving up yet. We're going to look at the second one and we ask, can it resolve with this one? The answer is nope, cannot, because T are both unnegated on both sides, so it's not going to negate, it's not going to resolve. And then we look at this one versus this one here. It is not going to resolve either because we cannot find a variable where it is negated on one side and not negated on the other side. And then finally, we look at this term versus this term here. It is also unresolvable. So we are basically just we come to the conclusion that no resolution be performed, and false is not in the CNF. So the conclusion, now this is mechanically what we have achieved, which is basically saying, oh, okay, there's not a single step of resolution that is possible in this case. But the conclusion is phi null is not a theorem. Now, I don't want to see people saying phi null is not true, because this is not saying phi null is not true. It is simply saying phi null does not follow psi. That is all it is saying. It is not saying phi null is not true. It is not a theorem, but just because it's not a theorem does not mean the expression is always false. So there's a big distinction between those two. Okay, so we got some questions. In general, when asked to prove a theorem, psi does not come from the theorem itself. Well, psi is representing everything that is known to be true, so that's usually coming from a different place, a different source. I thought the left-hand side of the implication was psi. Which implication? Which implication are we talking about? There's no implication in the CNF. You mean the theorem? The theorem just has an implication itself. That doesn't show anything. With this entire thing, T implies S and R is the proposed theorem. The proposed theorem is nothing more than just a Boolean expression, and the question is whether it is implied by everything that is known to be true or not. Okay. All right. T does not mean true in this case. T is one of the variables. I usually use 1 to represent true, not T. I mean, have been using that notation since the beginning of this class. Okay. All right. So now we are moving on to the second example, which hopefully is a little bit more interesting. Okay, so I'm going to use the math symbol again, because this one is, I'm going to call this phi1, because it's a different expression, and we want to know whether this expression is a theorem or not. In other words, is psi implying this or not? Alright, so now the first thing we need to do is to negate it. So let's go ahead and negate it, which is the negation of QR. QR implies T. And now we take a look at this and go like, what are we going to do? And it is important to put extra parentheses because I want to emphasize that we are negating the entire implication itself. So we start with negating the theorem that we're trying to prove. And the first thing we need to do is to get rid of the implication, which becomes the negation of the left-hand side or the right-hand side, like so. And looking at this, I'm going to resolve the inner negation first. So I'm going to apply De Morgan's law, and it's only going to be applied here. So I'm leaving the outside negation alone. And this one, once I apply that, it becomes not Q or not R, because the conjunction has to change the conjunction has to change to become a disjunction. So we got this one, and then we look at this and go like, disjunction is associative, which means the extra parentheses in the inside does not really help us in any way. So now we end up with a longer disjunction, but it is inside the negation, so we don't have a CNF at this point. In fact, we have something that is rather messy. So what we need to do is to apply De Morgan's law. So De Morgan's law apply to a disjunction that has more than two terms, because it's basically just doing exactly the same thing. We distribute the negation from the outside to each one of the items inside the disjunction, and then the entire disjunction becomes a conjunction. So now we have basically not Q, and not R, and not T. And when you perform one last thing, which is simplification, we got Q by itself, R by itself, and then not T also by itself. So that is the CNF of phi 1. Do we have any questions about how, the negation of phi 1 becomes this particular CNF? So I have to re-emphasize, this is the CNF representing the negated phi 1. Because that's what we need to form a conjunction with psi, and then do the resolution until we get to a contradiction or until we cannot go any further. All right, so there are no questions at this point. Very good, then I shall move on. All right, so at this point, we're going to say, okay, let's make a super CNF again. All right, so we have our super CNF. So the super CNF is really the concatenation of everything that is known to be true. So I am going to borrow that from here because it's the same thing. Psi has not changed. So we're going to have psi the same way over here. and we are going to concatenate with it using a conjunction the CNF that is representing the negated proposed theorem, which is the negated, which is not phi 1. Okay, the negated version of phi 1, which is this. And now we try to perform resolution. All right. So same as before, whenever you want to perform a step of resolution, you have to find two disjunctive terms where on one side we have a variable, some variable, and then on the other side we have the same variable except it is negated. We already investigated between the first and the second, and we could not find anything that is resolvable, so we're going to skip it this time. But if we look at this one and this one, it seems to be resolvable. All right, so I'm gonna try to make it easier to understand. So we'll see whether that works or not, because I'm not sure whether it's gonna line up or not. It does seem to line up. Okay, so I'm gonna line up this one. Oh, it's off by 1. Okay, there we go. It's off by 1 space. I don't understand why, but that's okay. It's the visual effect that I want. So I think that should line up too. So just focus on the right hand side. I'm just typing on the left hand side, but what you need to do is to focus on the right hand side, because otherwise it can get pretty confusing. So right now we have resolution. I cannot do bold when it is inside a pre-formatted block. I can do bold if it is not inside. And let me see. Oh, I can do underline. That's right. Okay, so underline may be easier to read. Give me a second here. All right, so get rid of those. And I'll do underline here. So this is one item. Okay, maybe underline, 2 underlines. Oh, just don't do boldface. How do I do underline in Markdown? I'm pretty sure there's a way to do it. Now I am a little obsessed and have to find out. Markdown, underline. I thought it was a single underline. Yeah, double underline is boldface. I guess it's just as well, okay? Your boldface is standing out too, so that's okay. I'm not gonna spend too much time in class to do this. All right, there we go. So I think that's pretty clear that we are going to use Q as the quote-unquote connector and then perform the resolution. After the resolution, we are basically concatenating the two, except anything that mentions Q is gone. So we are left with just not R or not S. All right, so let me do this. Copy, equal, and then paste. There we go. All right, so now I'm gonna get rid of the boldface, okay, because we're gonna try to resolve a little bit more. But before we do that, we're going to add the term that is the result of the resolution, which is not R or not S. So I'm going to pause here just to make sure that everybody understands why we have this extra term here at this point. This is an extra term that is the result of the resolution. The result of a resolution can be joined to the super CNF without any problems, because it is, after all, implied by the components that we used to perform the resolution. Yeah, it is technically not R or not S or false. So, but that's okay. The not false, the false is not needed here. The or false is not needed here. We'll need that later on when we are left with nothing. Now, what Jonathan is saying, for those of you who are kind of thinking like, where is that coming from? Because every single disjunction has an implicit or false in it. Because we have to use the or because, they are all disjunctions, but anything or false is preserving the original value. So if you are concatenating this part with this part over here, then, the technical result of the resolution is going to have the or false in it. And Wade is asking what extra term. So the extra term is this part here. This is quote unquote the extra term. It is the result of resolution. So the result of a resolution has to be added to the CNF because it is, it becomes one part of it, because we might use this for later resolution in order to come to the contradiction. Yep. Yep, that was Boolean algebra. We kind of talked about it already. Alright, so now we look at this and say, well, what can we do to perform resolution? So we're still looking at the first term and ask, what else can we do? Well, let's see. We got this Q over here. This not R can quite easily resolve with this R over here. So we're gonna do the we're gonna use that this time. Now, obviously, I'm just doing this in a very systematic way, and it's not going to be the quickest way to come to the conclusion, which is we can get to a CNF. We can get to contradiction, and I have no idea why it is why it's doing boldface. Let's see if I just add something here. There we go. I'm just adding it so that the boldface goes away. So now we are concatenating not Q or not R or not S with just R itself. But once again, R all by itself is really technically R or false. So we now end up with a new term which is not Q or not S or false. Okay, and then we can append it all the way to the end of whatever we had already. So I'm going to do a copy and paste into here and get rid of the unnecessary italic and also the boldface. But before I get rid of the boldface, I'm going to add this new term, which is not Q or not S. And if you want, or R. And then we get rid of the boldface because that's just for indicating what term we were using for resolution. Alright, so are we doing okay so far? I'm looking at the text channel. What if you choose the second part? Will the result be not R or T? Yes, if I choose to use Q as the quote-unquote connector, that's what it would look like. So it depends on what you're using as the connector. Alright, so we can keep doing it like this, except in this case, I think we can end this rather quickly. Okay, I'm looking at, so we got a not T over here, and then we have a T over here, and T is, I'm just looking at the quickest way to end this. So R or 0 is just R, and we can basically be left with this T if we resolve the Q and the R away. So I've been working on the first one, which is not going to be very helpful to us. But if I worked with the second one, it would end this whole thing pretty quickly. So I'm just going to do that here. All right, so we will use this not Q to resolve with this Q over here. All right. So the end result of this resolution. So resolution itself is a very mechanical process. So the result of this is really just not R or T is the end result of this. So I'm going to get rid of the boldface again. And this time we want to get rid of the not R. And that's pretty easy to do because we look at this R. And then we look at this not R over here. And we say we can resolve those two. And once we resolve those two, we end up with just T itself. So get rid of the boldface. Probably page up, page down thing. Yep, there we go. one more. There we go. So now we can see how we have this t as opposed to this not t over here. So when these two resolve, okay, now this time it is important to understand this is actually not t or false, and this is t or false. So when we resolve this one last time, then we end up with false or false, false or false. And let's get rid of the boldface again. All right. So at this point we have false or false, which simplifies to false. But in a conjunction, if you have one single false, then the whole thing is going to be false. So now we can now claim the whole thing is false, which means we're done with all the steps of resolution. But in this case, because the super CNF can resolve to false, we can now make the conclusion. Okay, I'm going to make the conclusion and then we take row. So conclusion is because resolution reaches a contradiction, the theorem, the proposed theorem, which is phi 1 in this case, is a theorem. There we go. All right, so we have a conclusion in this case. And then on, just put in a whole bunch of items here. Okay, so that would work too. So what on is doing is to number each part, and then when we have a resolution, it is clear which two we are using for resolution. How we are resolving the terms. So that would work as well. And that's a quick way to get to the contradiction. Mine is a little bit longer because I took you guys to the park and also the scenic route in that case. All right, so let's take row. So we're gonna take row, and let's see, where's row taking for today? There we go. All right, so we're gonna unhide it, and then the word is Joplin, Joplin. I just typed it in the text channel, copy and paste it, and that should be it. Okay, I'm just going to double check, but I'm pretty sure that's the word. Joplin. Pretty sure that's it. Yep, that's Joplin. All right, we got Jonathan typing. Nope, I have not tried Emacs. I guess I'm just not a very Emacs person. I encountered Emacs all the way back when I first started to use Vim, and at that time Emacs was called the memory pig, which means it takes up a lot more memory space compared to Vim or VI at the time. Vim came much later. I understand Emacs has all kinds of cool stuff, like lots of macro capability. You can even turn it into an operating system. You can stay in Emacs and do everything in Emacs. Yep. But I stuck with Vim, not Emacs. So. Yep, that's one way to start a religious war in computer science. Is I think one of these two is a better editor, and I think it is, and it just substitute that word, and it just watch the fireworks after that. It's going to be even more passionate. That discussion is going to be even more passionate than any actual discussion that is actually useful. If you are to say, between Python and JavaScript, which one do you think is a better scripting language? There will be a kind of like a civil discussion. People would bring up all the technical points and whatnot. But when it comes to editors, man, the gloves are off, man. Why bring VS Code to an editor war? Kind of the same thing as, why bring a pocket knife to a gunfight, that sort of thing. All right, so I think most people are done with the road taking thing, from the discussion in the text channel. All right, so now we're gonna get back to today's topic, finally. All right, so today's topic is about probability. And when we talk about probability, we got to understand two things. So we have to understand the outcome and events. Now, outcomes we got to already. Okay, when we talked about the big omega and the big U notation, those are the ways to actually generate, a set that contains all the possible outcomes of an experiment. And we also know how to count those things, and that's why we have P, for permutation, and then C for combination. So those are the ways that we compute the cardinality of big omega and big U. Events, on the other hand, is something that we have not talked about. So we're going to talk about events now. An event, on the other hand, is a subset of big omega. So that's the first thing, okay? And in this case, omega is the set of all possible outcomes. It includes both permutation and combination. It's just collectively we use omega as a representation to represent all the possible outcomes. So now an event is basically a subset of big omega. How events as sets are constructed depends on the application or probabilities. So there's no set equation to relate the event set with the omega. It all depends on what you want to accomplish. For instance, I'll give you an example. So for instance, if you say, if you make the assumption that lotto tickets, okay, each particular way of arranging the 5 lucky numbers and also the super lotto number, cannot remember the actual name of that, but assuming those things are unique, okay, what is the probability of winning the jackpot? Well, in that case, your event set has only one single element in it, because that would be the one with all 5 matching lucky numbers, plus also a matching super lotto number. The Powerball, that's it. The Powerball number also has to match. On the other hand, if you just say, I spent $1 to buy a lotto ticket, I just want to get something back, okay, maybe just $1. In that case, you have a much larger set, because according to the rules of the lotto game, there are many other prizes you can win. Okay, you can match like 2 out of the 5 lucky numbers. You can match 3 out of the 5 lucky numbers. You can match 4 of the 5 lucky numbers. You can match all 5 lucky numbers, but miss the Powerball number. Okay, so there are many ways where you can get back, at least $1. Okay, so in that case, your event set is going to be a larger set. So how E relates to omega is dependent on what problem you're trying to solve. Now, the most important point here is the probability is defined as the cardinality of whatever event set you want to use as quote unquote the interested outcomes, and also divided by the cardinality of big omega, which is basically all the possible outcomes. That is defined as the probability of E, probability of whatever event that you're interested in. Are we okay with these terms? The only new term that we have added at this point is the event set. And an event is basically just something of interest to you, and you want to figure out what is the probability that that is going to happen. So I just want to check, making sure that we don't have any questions at this point. Okay, the crickets have spoken. No questions. Or maybe there are questions. They're coming in now. Oh, is it clipping? I turned in the feedback already. Okay, let me try again and see. And this time I'm going to look at the meter. So this will be a good distance. Okay. There we go. Yeah, that might also pop a few tweeters. All right. Oh, that's my cat. That's a real cat. That's an actual real cat wanting to get out. All right. So we already talked about the birthday problem. He goes after lizards. Doesn't want to eat anything. He likes to kill things, but not to eat them. So lots of food waste around here. All right. So we talked about the birthday problem already, but let's go back and talk about it again because this time around, I kind of want to talk about it in a way where to answer some of the questions that you might have, which is how do we approach a problem? Okay, so instead of reading my notes, I'm going to be typing some new notes over here. And let me see if I can zoom in. We can zoom in indeed. That's nice. Okay. So we can zoom in maybe one more time. Control Shift equal, which is the plus sign. Okay, there we go. All right. All right, so we're going to do this as probability. Okay, there we go. That's a header. All right, so we want to solve this problem. Okay, so in other words, in general, okay, we want to solve the problem of what are the chances that at least 2 people in a class share a birthday. Okay, there we go. So that's the question that we are asking, and we want to be able to answer this question. So the first thing we notice is to answer this question directly is pretty hard, because if let's say you only have 3 people, okay, that's pretty easy, right? You would think that with 3 people it's pretty easy. So let's call these people A, B, and C. But if you want to answer the question of what are the chances that at least 2 people within these 3 people have the same share a birthday, you got a few configurations, because you can have A and B sharing a birthday, you can have B and C sharing a birthday, you can have A and C sharing a birthday, you can also have A, B, and C all sharing the same birthday. Those are all counted in as this particular condition here, at least 2 people in the class sharing a birthday. So that makes it kind of difficult to handle. On the other hand, if you look at the flip side of if it is not the case that at least 2 people in the class share the birthday, that turns out to be an easy thing to process, because what you're asking is what are the chances that everybody has a unique birthday, that no one shared birthday with anyone else in the class. And that turns out to be an easier problem to solve. So our event is basically trying to count the cases of this happening, but what we want to do is to work on the complement of the event. So the complement of the event, so we are looking at the complement of the event, and if I want to express this mathematically, this would be omega, big omega, minus E. It's the difference between those 2 sets. Okay, so we're going to work on this one instead of E itself, because E itself is too complicated to account for all the cases, and as it turns out, the complement is super easy to work with. All right. Yep, exactly. So Aman is 100% correct here. It is like grabbing birthdays within a bag, but there's a little spin to it, right? Because then the question is ordering important or not? Okay, because normally if you're grabbing some numbers out of a bag without replacement, the first question to ask is what about ordering? So to understand whether ordering is important or not, okay, the best way to look at this is to think small. Okay, think about you only have 2 or 3 people. 2 may be two will work, okay? However, three people will make it work even better, because I think it illustrates the ordering thing even better. So let's go ahead and take a look at three people. Okay, so we'll make an assumption. Let's say a class has three people, and we have person A, person B, and person C. And we want to find out, how many ways can we assign unique birthdays to A, B, and C. Okay, so because the question is, whether ordering is important or not. So let's say we have just chosen. Okay, we choose three specific dates. Okay, January 1st, New Year's Day. Let's pick. I'm trying to pick some April's Fool's Day. There we go. I want to pick basically dates that are special but not related to anything that people can argue over. What other day can people not argue over? I know, solstice. So winter solstice is, I think, December 22nd. Let me double check. Winter solstice is December 21st. Okay, and that's the same every year. So we have December 21st. Okay, so we got these three dates chosen, and they are unique, right? But the question is, there are three possible ways to arrange this, because we can have person A choosing New Year's Day, we can have person B choosing April's Fool's Day, and then we can have person C choosing winter solstice, or we can have person A choosing April Fool's Day, person B choosing winter solstice, and then person C choosing New Year's Day, and so on. So okay, so all of these count as different cases, right? They are different elements of the event, because so there are more and more of these. So now the question is, what is omega? Okay, omega basically is just every single possible way for three people to choose their birthdays, and they can be the same. They may not be the same, but they can be the same. So omega includes the following. It includes A, B, and C sharing New Year's Day, and so on. So in this case, I think it becomes clear that ordering is important, okay? Because who gets New Year's Day, who gets April's Fool's Day, and who gets winter solstice does make a difference, okay? Because all of those are counted differently. There are 6 ways to arrange these 3 specific dates that we have chosen. All right. So let me take a look here. And because people are unique, yes, because who gets which date is important, and as a result, ordering is important in this case. So because ordering is important, the cardinality of E of the event, okay, I'm going to use math notation here. So the cardinality of E is going to be the permutation of starting with 365 days and choose 3, and then the cardinality of omega, on the other hand, is easier because it's just 365 days to the power of 3 in this case. All right, so let me just pause here and see if you guys have any questions. Because what I'm attempting to do is to go through the reasoning of why we have chosen the permutation of choosing 3 out of 365 as the cardinality of the event. Why isn't it cardinality of omega is 365? I thought it is. It's 365 to the power of 3. I'm not sure what Jonathan is asking. Oh, cardinality. Yes, I forgot about the cardinality of omega. Not omega itself, but the cardinality of. There we go. Thank you. That is correct. Because we are counting the number of elements, because omega itself is not a number. It is a set of, in this case, tuples. All right. Any questions about this portion here? Actually, I lied. Jonathan, you didn't catch me making this error here. Because E is not this, right? This is the complement of E. So I really need to say that this is actually the complement of E, which is omega minus E. So I lied again. There we go. This is actually omega minus E. And this makes the probability of E the following. So it's basically 1 minus the fraction of P 365 divided by 365 to the power of 3. There we go. And the fraction is missing the bar in between, which is interesting. I don't see why it would be missing that, but it is missing. See this here? There's no bar in the fraction. Suppose I can change the notation and not use fraction, and instead we can use just plain old division. There we go. Oh, it could be the zoom. Yeah, it could be that too. I'm not really sure whether it's a zoom or not, because the output of LaTeX is supposed to be scalable. Okay. But do we have any questions about how this math is working out? Okay. All right. All right, so let me take a look at the time. All right, cool. All right, so this is one type of probability, and then there's another type of probability for analysis. So this one has to do with, the best example is basically flipping a coin, okay? Because you need the setup so that it is with replacement, and in each trial only has 2 possible outcomes. Now this is particularly interesting to computer science because when everything is binary and everything is either true or false, you can call it Boolean or you can call it binary, basically the same thing, because all you're saying is whether the result is a 0 or 1, whether it is a false or true, or head or tail. Basically any time when the outcome of a single trial is only has 2 possibilities and it is with replacement, which means every single trial gets to choose between those 2 as its outcome, then we have a different type of probability distribution. Okay, this one is, I'm gonna type coin flipping, okay, because coin flipping is the best example of those things because it's easy to see, visualize, and it's also easy to kind of relate to, because in real life, we can play these games. So with coin flipping, let's say we flip a coin 5 times, okay. The question is, I don't really care about the ordering. I just want to do a count, okay? How many times do we end up with a head and how many times do we end up with a tail? Okay, so we'll just ask, how often, I should say, what are the chances? What are the chances that we get 3 heads and, 3 heads and 2 tails? And ordering is not important. So how would we answer this particular question? Well, first thing is, we probably want to just kind of visualize and say, okay, all of these things, are counted as the event. Okay, so we can have head, 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 tail, tail. We can have head, head, tail, tail, head. We can have head, head, tail, tail, head, head. We can have tail, tail, head, head, head. We can have head, tail, head, tail, head. We can have, let's see, what else do we have here? So we can have, a bunch of these. Okay, the first question is, how many are we talking about? Okay. All right, so let me get to the text channel here. Multiply. Nope. Nope, it's not just multiply. We want to count. Okay, the first thing is, how many ways can we arrange the head and tails? So given that you have 3 heads and 2 tails, okay, how many ways can you arrange these things? Any quick answers to do this? It is not 2 to the power of 5. But you got the 2 numbers, you got the 5 and the 2, it's just not 2 to the power of 5. And then Jonathan C is saying you can arrange it 5 ways. Nope, there are more than 5 ways to do it. Let me give you another way to do this. Okay, so at this point I have only explored all the ways when the tails are stuck together, and then at this point we start to look at they can be spaced out. So we can have head, tail, head, head, tail, right? And then we have tail, head, head, tail, head, and so on. So the question is, how do we analyze this, right? I mean, how do we know how many ways can we do this? Nope, it is, well, I'm not sure whether it's 10 or not. I don't think it is. You're brute forcing your answers. Okay. Okay, so, aha, finally, Adam is correct. 5 choose 2. Okay, so the number of ways to end up with 3 heads and 2 tails is, and I'm going to use the fancy math thing here, it is 5 choose 2. Okay, then you guys go like, what? Why is it 5 choose 2? Yeah, it might be 10. Well, let me see. 5 choose 2 is 5 divided by 2 factorial times 3 factorial. So that is probably 10. Yep, there we go. But it is not because of 5 times 2. Okay, it turns out to be the same. Okay, 5 choose 2 turns out to be the same as 5 times 2, but it is not because of 5 times 2. It is because of 5 choose 2. So the question is, why? I don't understand how this has anything to do with combination, and combination has to do with set notation too. So how do we relate all of these things, right? So let's think about this. Okay, so I'm gonna give you guys a way to encode it. Okay, so let's think about how to encode. Okay, encode a way an outcome. Okay, and encode an outcome of 5 coin tosses where ordering is, okay, I'm just gonna as tuples. Okay, so we're gonna have a new way of encoding, because typically we use tuples, right? This is head, 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 tail, tail is a tuple, head, head, tail, tail, head is a tuple, and so on. So instead of using tuples, I'm gonna choose a different way to do it. So I'm going to say use for each one, for each experiment outcome, use a set to denote when the tails happen. Okay, All right, so that looks kind of vague and kind of like, okay, I'm not sure really what you mean by this. Okay, so we're going to use the zero-oriented way of counting, which is how most programming languages are. So in this case, this is now encoded as 3, 4 as a set. This one here is encoded as what? 2, 3. This one here is encoded as 1, 2, and so on. So let's pick one that has an interleaving. This one is 1, 3. This one here is 1, 4. And then finally this one here is 0, 3. And so on. So are we doing okay? Does everybody see how I am converting something that in nature, okay, when you look at it intuitively, it looks like a tuple, but I'm switching the representation into using a set, because all I'm doing here is to say, okay, let's just focus on the tails, because if it's not a tail, it is a head. So if I just know where the tails are, I implicitly know where the heads are too. So if I only focus on the tails, I can now say, okay, where did the tails happen? It occurred in trial number 3 and trial number 4. Okay, so that means the rest are heads. So are we doing okay so far with this new representation of how we are encoding a specific outcome of an experiment that consists of 5 coin tosses? Yes, complement with the E. Okay, so the 3 is the index of one of the tails, and then the 4 is the index of the other tail. The 2 is the index of the first tail, and then the 3 is the index of the second tail. Is that okay, Jonathan? W. Okay, all right. So, finally, we have a set of 2, right? But for this particular set, okay, how many are out of the bag? Okay, what is the size of the bag that we are choosing 2 out of? It is a bag that has 5 items, right? Because the 5 items would be 0, 1, 2, 3, 4. Those are the 5 possible locations where a tail can be. And then for each one of the outcome, we are simply saying, just pick 2 of the 5 numbers in the bag, and that becomes the way that I'm encoding, the positioning of the tails. Is that okay? All right, cool. All right. So now this ends up to be something that is also related to binomials. You go like, binomials. We are all over the place now because we first start with tuples, and then we have a way to encode it using a set, and now you're saying this has something to do with binomial. Well, let's think about it this way. Let's say P is the chances of a head after a coin toss, and then Q, which is 1 minus P, is the chances of a tail. So I'm just randomly picking 2 constants, okay, 2 names. P is the chances of ending on the head, and then Q is the chances of landing on the tail. Normally, if a coin is not loaded, they should be the same. So if I were to toss a coin 5 times, okay, then we end up with P plus Q. Okay, let me use math equations here again. P plus Q, the whole thing to the power of 5. This would represent all the possible ways, right? So within all the possible ways, okay, we have some number. I'm gonna call this K0 times P to the power of 5 plus K1 times P to the power of 4 and then times Q plus K2 times P to the power of 3 Q to the power of 2 plus K3. Let me just finish this. I know this is taking a little bit of time, but let me finish this while you're thinking about where this is going. Now, obviously, to those people who actually read the notes ahead of time, they look at this and go like, yeah, we know exactly where this is going. This is boring. Okay, and then the last one is K5 times P, no P, but Q to the power of 5. Alright, so let's just take a look at this. Okay, you just have to focus on the right hand side. You don't have to look at how I type this entire thing out. But if you just look at the right hand side, does that make sense? If I give you, if you just say the P and Q are just two constants, okay? Or for those of you who just cannot look at this as P plus Q, all you have to do is to switch this to 1 plus X, okay? And P is 1 in this case, and Q is X in this case. Or you can say X plus Y, okay? But I'm going to keep P and Q here. There we go. Does that make sense? For some K0, K1, K2, all the way up to K5, this is how we can expand P plus Q to the power of 5. Are we good so far? All right, because this is just math stuff, right? So now the next question is, what is K0? What is K1, K2? How do we know how to calculate the constants, K of I, right? So K of I, in this case, is basically 5 choose I. Okay, it is 5 choose I. So I want you to think about this and ask, does that make sense? Does that make sense to you that K of I, which is the coefficient of P to the power of something times Q to the power of something, is really just 5 choose I? Does that make sense to you? When you look at this, it may not make sense, right? But when we look at this from a simpler view, it might, help you understand something that you have seen already. So we'll just look at 5 x plus y to the power squared. It is x squared plus 2xy plus y squared. Right? I mean, that's something that you have learned a long time ago. So when we have x plus y to the power of 3, what do we get? We have 1 of x cubed, and then how many x squared y do we get? We have 3 of those, right? So we have 3x squared y, and then we also have 3 of xy squared, and then we have only 1 of y cubed. Does that make sense? Are we okay so far? Is this reminding you of some math stuff that you have already understood? Okay, very good. So we look at this and go like, I still don't get where this is going. Okay, I'm not quite seeing where this is going, because it doesn't really matter what the coefficients are, because all of this is guaranteed to add up to 1, because that accounts for all the possible cases. So why are we so picky? Why do we want to pay attention to the coefficients of each term of this addition? So that becomes the next question. I'm looking at the time. We got 5 more minutes. Well, we want to know this because if P and Q are not the same, and we are interested in having at least 2 heads or at least 3 heads and so on, then we have a way to calculate those things. So let me just pose a particular question here. Okay, so I'm gonna say, what are the chances chances that out of 5 coin flips, 2 land on heads? Okay, so this is the question. So assuming that we're observing someone flipping groups of 5 tosses. Okay, 1, 2, 3, 4, 5. Make a record of it. 1, 2, 3, 4, 5. Make a record of it. 1, 2, 3, 4, 5. Make a record of it. And I'm only interested in the chances of out of 5 coin flips that there are exactly 2 heads. How do we calculate that probability? So in this case, the probability is going to be pretty easy to figure out, because the probability is now we got 5, choose 2, and because we have already defined P to be the chances of landing on a head, so in this case we would have P to the power of 2 times Q to the power of 3, because the other 3 are guaranteed to be tails, because if it's not a head, it has to be a tail. So now we have a way to do the calculation, the probabilities. Yep, so Jonathan is correct. It is 5 choose 2, but we also have to remember that we have to multiply 5 choose 2 to P squared, because we have 2 heads, and then Q to the power of 3, which are the tails. Alright, so you look at this, okay, and I know we are quickly running out of time, but we are also going to contrast this, okay? So we are going to say, what are the chances that out of 5 coin flips, 2 land on tails? So you go like, oh, that's pretty easy, because all we have to do is to copy, paste, and modify. Okay, because that means we have 3 landing on the head and 2 landing on the tail. Okay. And if a coin is not loaded, then these 2 would be the same. Does that make sense? Does that make sense that if a coin is even, the chances of landing on the head and the tail are the same, because P and Q would be exactly the same number in that case. So we are basically just looking at P to the power of 5 in both cases. 5 choose 2 and 5 choose 3 are exactly the same thing, which is 10 in this case. So the probability would be exactly the same. So after you make a whole lot of observations, what if the observed probability are not the same? The one is greater than the other one. Then you can come to a likely conclusion that the coin is loaded. Alright? And in computer science, there are a lot of cases where the coin is super loaded. Okay, it's really going to one side a whole lot. Because when we look at P as the probability of a bit, okay, a binary digit transmitted and received correctly, and Q having that bit not received correctly, then if that was the quote-unquote coin, then it is really, really loaded, because we really want P to be 99.99999%, and Q is basically 1 minus that, right? But in a noisy environment, it may not be as ideal as 99.99999%. It might be 99%, okay, which means you still have that 1% chance of a bit not transmitting correctly. Then why do we care about counting the number of bits not transmitted correctly? Because there are certain ways you can have cell correcting code. It can correct up to so many bits within a packet. So if you're exceeding that many of erroneous bits, then it cannot help you. Then you have to retransmit the packet. So you're basically looking at a trade-off of including some additional information for error correction, as opposed to retransmitting. And whether it is worth it to transmit extra bits for self-correction or not really depends on how likely is it that you will have an erroneous reception of a bit that is transmitted. So that's basically one particular application of how we use binomial distribution. But in reality, every single time when you are dealing with experiments where each trial comes up with 2 possible choices, then you are potentially looking at a binomial distribution. Alright, so we are running out of time today. I would like you guys to read the rest of this module. Now, what I have described up to this point is basically just a basic setup of all the math stuff. But I want you to take a look at Pascal's identity. Okay, Pascal's identity is looking at n choose k plus n choose k minus 1, and it turns out to be the same thing as n plus 1 choose k. That turns out to be quite handy. This is why we have Pascal's triangle, by the way. If you're familiar of Pascal's triangle is the result of Pascal's identity. Are you surprised? Not really, because they're coming from Pascal, right? But in this particular module, Pascal's identity is nothing more than just a tool to help us prove something else, and that would be the binomial theorem. And the binomial theorem basically says, p plus q to the power of k is the summation of I equals to 0 to k. K choose I times p to the power of I, q times k, q times q's to the power of k minus I. Oof, okay, which is something that we just looked at, okay? But this one is far more general than just saying, oh, we have 5, p plus q to the power of 5. This is generalizing to, let's raise it to the power of k, okay? And how do we prove it, right? Well, this turns out to be also a different technique of proving. This is proof by induction, okay? Which is something that we're going to talk about on Wednesday. So you got to read all the way through to the end. And then on Wednesday, we'll get to a new proof technique, which is proof by induction. And by the way, proof by induction is super useful when you're dealing with recursive definitions. And we're also going to take a look at, the binomial distribution and also Pascal's identity. So those are the things that we're going to do on Wednesday. Are there any questions? All right. Well, if there are no questions, have a nice evening, and I will see you guys on Wednesday. And by that time, I will definitely have the first exam graded, and your score would have been sent to you by email. All right. Thank you. And I'm going to sign off from the live channels, but I'll still be online because from 6 to 7 is my office hour. So for those of you who have questions, now is a good time to ask.